Okay, so this is a stress analysis on our home-built tank that we constructed over about a week period from drawing board to first, wouldn't call it finished product, but it was functioning at least. We will be looking specifically at the moment given by the torque on the hydrostatics, because this is a basically lawnmower chassis set on top of a home-built or home-constructed chassis, mower body, I guess. Has a 20 horse Kohler command mower engine, vertical shaft, using two hydrostatic zero turns hydrostatics that are independent of one another. And then in the rear we just have a straight axle, so that's not really crazy as far as stress analysis, but yeah, I guess we can move on here. This is the chassis. I designed it in SolidWorks and even hollowed out all of the members to the correct measurements that I checked with the caliper on the actual machine. Basically, it was made out of three sizes of tubes. We have the smaller tubes back here that are 1.5 inches square tubing. We have the main structural tubing, main frame rails, I guess you call it, over, as you can see in this other picture on the right. That is a 2 3/8 inch square tube. And we have the center members, which are 3-inch square tubing. I believe that all four in the middle are the 3-inch. And they all have different sidewall depths and stuff, so that's something that will kind of be included in our stress analysis. So first and foremost, we had to figure out engine speed and torque involved. So what I did was I took a strobe light that we had that was able to, tell me what the RPM of the engine was, and did a test at full throttle, and it came out to be around 3,200 RPM. That's kind of tentative because the engine wasn't quite running right at that moment. It was functioning and it was able to do work, but I wouldn't say it's peak torque, but we're going to assume it is for this scenario, I guess. According to the online torque specs of the engine and the torque curve, we ended up finding out to be around 39.9 foot-pounds. So the next thing was to figure out how fast the wheels are spinning at full speed, and then this is in forward, and that ended up being around 90 RPM. This test was done basically putting a piece of tape on the tire, driving it forward, taking a video. Pretty simple, just took a little extra time, that's all. So here's kind of the work, the problem we have to go through here. As you can see, this is the frame rail we're looking at, and this is kind of the idea of what's happening at that frame rail if everything was static. So basically, like, you're putting the hydrostatics in full or top speed, I guess, position, and you have the engine all the way up, governed all the way up. So max torque is coming out of the motor, and max torque consequently coming out of the hydrostatics, getting 19,000 foot-pounds coming out of there. As you can see, I calculated it by timesing the 39.9 foot-pounds of torque coming out of the motor at the shaft by the rotation ratio between the engine and the output of the tires. So basically kind of looking at that ratio to get the foot-pounds. Ended up being 1,596 foot-pounds, or 19,000 foot-pound inches, or pound inches. We also have to add in track tension because we have basically artificial tension going on. I'm assuming it's around 200 pounds because I think there's a lot of tension there, to be honest, way more than 200 pounds, but the outer tensioning rod here is handling about half of it, so 200 pounds is a pretty reasonable estimate. So now we know kind of what we're looking at here for a moment, And what we're looking at here for linear compression, can move on to calculating the stress at that point. So this is the point we're looking at, the top of the frame rail, not the bottom, because that would be under tension and it would cancel out a little bit with the compression, that 200 pounds of compression. So this is going to be max stress in our rail and where it's most likely to fail. So first thing I had to find was the area. Remember, this is a 2 3/8 inch square tubing, and it had a thickness, wall thickness of 0.065. So that ended up coming out with to 0.6 inches squared. And then I had to find the moment, which is moment of inertia, which is pretty simple. I mean, it's just a square. So the outside times minus the inside, 0.5346 I ended up with, and that's equal in the x and y. So we took the output torque times the distance from the center all over the moment of inertia, and that ended up being 42,542 psi. Remember, we had to add in the compression, which was 200 divided by 0.6, it's 333.33 repeated. Those together would give you 42,875. So that's pressure at that point on the frame rail. Now that's kind of a problem because the yield stress of this mild steel I'm using is only 36,200 psi. So technically, theoretically, at that point, we'd be suppressing yield. Not quite ultimate tensile strength, but definitely would not want to run it very long like that. And if we were going to actually engineer this, it would be a significant problem. So basically, I went through and just covered my bases, trying to figure out a way to make it work. So what I did was I replaced the 2 3/8 inch tube with the 3-inch tube and just recalculated it. Came out to be 17,657 psi, which is obviously pretty much half, maybe even a little under half of the yield stress. So that's plenty within, I don't know what you want to call it, safety area. So basically what we do if we were actually going to engineer this, we would go away with the 2 3/8 inch frame rails on the outside and just go all 3-inch tubing. Probably be a little easier for welding, and you'd have less open spots and stuff. So it would be better overall, I believe. But the stuff that we did use was just stuff we had on hand, so it wasn't really engineered. It was, done within a certain amount of. I've done this in the past, and this seems like it'll work. So I put together this little video, just kind of give you an idea of what this machine's capable of and what we've done with it. And it hasn't failed at all. We've used this machine quite a bit, so get into it. So, I mean, it's certainly been under a certain amount of stress. I would believe that there's many other parts that would fail before the frame rail would, such as the belt going to the hydrostatics, or probably the hydrostatics themselves. The seals would blow out inside of them, or fill in the blank. There's a lot of smaller, intricate parts in the drive system that would fail before it hit 1,500 foot-pounds, I believe. Yeah, I mean, other than that, if we were going to go engineer this better, I would probably consider using 3-inch out of plenty of other reasonings, not just the fact that it's would be better stress-wise. So then sources, there was one more, but I believe there was a reason I didn't list it. So other than that, thank you for watching and have a good one.